square is simulated by solar lamps, which give that solar light through the glass and all. So we simulate the actual hot condition and then we perform the test. So currently, like Tata Motors is having a full vehicle chamber, and almost all suppliers they are having their full vehicle climatic chambers, in which we can do both cold and hot ambience, ranging from -40 to +55 degrees Celsius. So just a brief introduction that Subramaniam was already told. So I will not take much time. Like I joined as a 2006 as a GT in Mahindra. Then 2 years I worked with Tata Motors, and currently I am working with Force Motors in vehicle development and testing, basically into thermal systems. So just to give you like brief on some projects which I work, like in Mahindra I was working like together with Subramaniam. I was working on this XUV 500 vehicle. So I was taking a lot of different systems like HVAC, like cabin cooling, engine cooling for the radiator development, radiator and cooling system development, and exhaust and after treatment and air intake system. So further, I worked for the XUV hybrid vehicle. So in addition to the engine, it is having a motor, and there is a requirement of cooling the motor, and there is a battery which runs the motor. And of XUV hybrid, the battery cooling was done by the conditioned air from the cabin. And there is a power electronics, lot of power electronics are there, which controls the motor, battery, and DC-DC converter, like from the high voltage of the battery to convert the voltage to the operating voltage of the components. So cooling of that motor cooling unit is also there. So there is this thing, a power electronics unit, because mostly the engine cooling system, the top tank temperature will go up to 100 degree or temperatures. But the operating temperature for the battery is in the range of 30 to 40 degrees Celsius, and for the power electronics, usually the temperatures has to be maintained at 60 degrees. So there has to be a separate radiator and electric pump, complete separate cooling system for the power electronics cooling. And in my Tata Motors, I have worked in the full vehicle climate chamber. So they have two climate chambers, one hot chamber. There the temperature can be taken up to +55 degrees Celsius, along with the solar simulation and the road load simulation. And they have even a cold chamber to test the cold ambient performance, like a cabin heating performance, demisting performance of the vehicle actually. So currently I'm working with Force Motors. So here I am involved in both diesel engines and electric vehicle thermal system development and testing actually. So thermal system development challenges and trends. So what are the, just a brief on the development trends and what are the new which is happening in the thermal system, like higher there is a higher cooling demand because of the higher power engines, like as you say, power of the engines are increasing because of the higher demand of vehicle speed and performance. So because of which there is a higher demand of the cooling system. So bigger radiators and higher performance cooling system is required. And there is a lesser front opening area due to styling and aerodynamic requirement to reduce the vehicle drag and all. So additional components like diesel particulate filter, ACR, etc. is getting added for the regulation norms. Like currently, because of the BS6 regulations, there are additional components like diesel particulate filter, which filters the exhaust gas from the soot, and then once the filter is fully clogged, and then there is a regeneration happens, like by adding the extra fuel, the soot particles are burned, and then um, it is exhausted. So there is a lot of heat regeneration happening. So there is additional requirement of heat shields and insulation material to protect the nearby components and heat transfer to the cabin. And there is a selective caloric reduction where urea is injected to the exhaust line, and then the NOx is converted to the less harmful gases. And uh, electrification and control logics to improve the cooling system performance is coming, like electrification of the thermostat, radiator fan, and a lot of electrification of the components is happening to improve the performance of the vehicle. And cooling logics, like initially we used to have the fixed engagement fans. So now to operate the components at whenever only it is required, like when coolant we have defining logics to ensure that the fan is operating only in the required condition, like when temperature goes to above the limit of 95 degree or 100 degree, or vehicle speeds are too less. In that conditions only we will be operating the vehicle to improve the power consumption and uh, reduce the loss of power and improve the fuel economy of the vehicle. So new refrigerants like R1234YF and the dual loop cooling system are coming to reduce the global warming potential. Like R134YF is a new refrigerant which is already implemented in Europe, and it is coming to India also. So which is having a lower GWP value compared to the existing R134A gas actually. And the dual loop system has two loops. In one loop there is a exhaust, there is a refrigerant gas, and there is a secondary loop of water. So there is less requirement of refrigerant. So we can reduce the quantity of refrigerant. So in secondary loop it will be water, and heat exchange happens between these two loops with a chiller unit. And there is a higher demand of meeting passenger comfort with reduced noise and power consumption. So that's a challenge. And as I told before, that there are additional cooling loops are coming for the power electronics and battery cooling. So these are the new developments which is happening in thermal system. So I just come to like typical new product development cycle. So typically we have 5 stages in a new product development cycle. So we have the planning. After the concept is made, concept approval, program approval. This is the planning phase, and then we have the design and development. The part modeling is done in CATIA, and simulations are done. And there is a process development, like what process the parts has to be manufactured, and that manufacturing process at the supplier end and at the for the vehicle manufacturing, that process design and development. And then validation is done, and then finally the production is done. So this is typically the 5 stages of advanced part called planning or the new product development system. So this is the detailed view of, this is the one which is a new product development cycle which is followed in Tata Motors. So the 5 stages which I told before, it is subdivided into different gateways, and the gateway sign-offs are done. Like after the concept phase, there is a concept validation is done, design is made, then simulations are done, and then at different stages it is checked that it is meeting that stage requirement, and then the product goes to the next phase and till the production happens. So in the different stage, different prototypes like mule, climate prototype, validation prototype, and production prototypes are made at the different stages with improvements in parts, and validations are done in the different stages to improve and meet the performance to the requirement level. So typically the complete product development cycle takes 4 to 5 years for completely new development. So this is a measurement system analysis, like the process development which I told. So like the product variations, reproducibility, linearity, all these things are checked during the process design and development. So these are the simple targets, like the precision to the tolerance ratio should be less than 10. These things are checked for the parts which are getting made at the supplier end, and also at the OEM level. So here you see a vehicle electric bus. So nowadays we are seeing a lot of buses, like electric buses are in the field. So it is having like in addition to normal diesel engines, it is having a battery cooling system, either cooled by a refrigerant cooled or coolant cooled, or maybe cabin conditioned air is used to cool this. Uh, so motor cooling loops are there to cool the motor, and power electronic cooling is also there in addition to the cabin cooling requirement. So as you say, in electrification there is much more challenges are there for the thermal system, and there are a lot of new systems and parts are coming for meeting the thermal demand. So here you see a hydrogen fuel cell vehicle. So the hydrogen is hydrogen. This hydrogen fuel cell, hydrogen and air reacts, and then the power is generated. So the heat rejection of the these hydrogen cells are more compared to the existing diesel engine vehicles. So there is a higher demand of bigger radiators and cooling demand. Also, the coolant temperatures in the hydrogen vehicles are lesser by 20 to 25 degrees Celsius compared to the diesel engine. Like the peak temperatures in diesel engine goes to 95 degrees Celsius, whereas here it is in the range of 70-75 degrees Celsius only. So the thermal efficiency of the radiators are less. Hence, we have provided bigger radiators and more efficient cooling system is required for the thermal management of the hydrogen electric vehicles. And even the low temperature operation of the hydrogen vehicles is also a challenge because of the formation of ice and flow restrictions in the fuel cells actually. So here, if you see, these are the different type of batteries which are being used. Like cylindrical batteries are there, prismatic type, like pouch type, and rectangular shape. So different manufacturers are using different shapes of battery. Like Tesla is using a cylindrical batteries, and BMW, others are using other kind of battery. And there is even different cooling systems are also different. Like there is a liquid cooling by providing some channels. There is a cooling by the chillers and a refrigeration system, and there is a immersed cooling. So different technology for cooling also is coming to meet the requirement. And so it's a, like a thermal system is a really challenging, and a lot of new developments are happening with the new technologies which are coming to the market. So here, if you see, this is a cooling like a thermal system of a Jaguar I-Face vehicle. So if you see, it is very complicated. If you see, like in the sense, there is a battery cooling. So here, if you see, there is a chiller is there, and through the chiller, your battery is liquid cooled, and there is a lot of valve mechanisms to route the cold fluid to the required part, like either battery or maybe the power electronics or cabin cooling. So with combinizing the condenser and evaporator, chiller. So if you see, the systems are become more complex, and a lot of it is ECU driven, and valves are controlled to meet the requirement of different systems. So new electric vehicles are like having a lot of thermal challenges, and a lot of new technologies and developments are coming to meet the requirements of the system and to improve the performance. So, coming to the typical product development cycle. So, like in the initial, there is initially the benchmarking is done. Like when we were doing XUV, also we'll identify the benchmark vehicles. Like for XUV, the Santa Fe vehicle was the benchmark. Hyundai Tucson, those were the vehicle taken as benchmark vehicle. So there are different sites like A2 McEwen which provide us the benchmark data. Like for the radiator size, fan size, front opening area are the critical benchmarking parameters for the cooling system, engine cooling system. Additionally, we the performance of the vehicle and tear down is also done, and measurements are taken, tests are taken to set the benchmark. Like mostly some like companies making a new vehicle in a particular segment, benchmarks are identified, those tear downs are done, measurements are done to ensure that we are either meeting or surpassing the existing vehicle in that category. So benchmarking is a very critical process in the typical vehicle development cycle. So here, if you see, like this is a Hyundai Audi A8 vehicle. So if you see, there are a lot of shroud cutouts are provided on the in the radiator shroud. So these shrouds has flaps. These flaps remain closed in the low velocity, and at high velocity, these flaps open and to reduce the flow restrictions. So by with benchmarking, we can get come to know the different features which our other benchmark vehicles are using, and which we can implement to improve the performance of the system. So system and component sizing. So like at initial phase, lot of calculations are done to understand how much is the actual heat rejection to the system, which is required for the cooling system. So those calculations are done, like for typical power of 105 kilowatt, like that is XUV power, XUV 500 vehicle engine power. So typically around that range, like the 100 kilowatt of power has to be reduced. Additionally, there will be heat rejection from the cabin cooling. That condenser also release heat to the radiator, and then there will be heat addition because of the intercooler heat rejection. So these calculations are done, and calculations are done for the typical heat exchanger size requirement, based on that heat rejection of the system, that what would be the size of the radiator, length, width, tube, variance, and we will calculate the typical heat exchanger dimensions, and these data are shared to the supplier, and supplier, based on their like their parts which are existing available with them, or with slight modification, they suggest as a part for the development. So once we give, like this is a 1D simulation, there are a lot of 1D simulation tools like Magna Coolie, and AV Magna Coolie is there, and different 1D simulation softwares are there, which simulate the performance of the cooling system before we have the actual CAD part is available. So we have the test data from the suppliers, like coolant pressure drop versus flow, internal flow, and air pressure drop versus the external flow, radiator heat rejection versus coolant and air at different airflow rates and coolant flow rates. These data along with the uh, component specifications are given as an input to the 1D simulation softwares. In addition, the engine heat rejection curve, like what is the heat rejection at different RPMs, and power, what is the heat rejection, these inputs are given to the 1D simulation tool, and the performance of the vehicle in actual driving conditions, like max power condition, max torque condition, the system sizing is done to with the 1D simulation tools. So Magna Coolie is a software which is a 1D simulation tool which is used by most of the OEMs, and it gives before the parts are available, it gives us a very good opportunity to explore and to size the system to the required performance. Now coming to the 3D CFD simulation. So once the design is done, and we have the CAD parts, 3D CFD simulations are done in ANSYS, Fluent, and other software. So like for the cooling system, front end air simulation is one critical parameters. Uh, so air guides and seals are provided to improve the airflow in the front end. So LSID, if you see, the airflow is in the lower range. The blue color you see in the range of like 0.8 to 1 meter per second only is there at the front of the front end module. And with by providing the air guides and seals, the flow leakages away from the front end module are reduced, and the front end flow is improved with the providing air guides and seals. So this CFD simulation tools give like before the vehicle is available. Once the design is done and the vehicle is not available, so this give us opportunity to optimize the performance of the system by reducing the flow deviation away from the module and to meet the required target. So we'll have typical targets like in the max power condition when vehicle is running in the full load. So we should have around 8 meters per second. By based on our past experience, we have this target, and by the CFD simulation, this we try to achieve these targets. So for max power condition, yeah, so we have typically targets of around 3 meter per second flow in front of radiator. So the maybe single fan or dual fan or the fan wattage requirement, those things are finalized to meet the target requirements of the system. So here if you see there is a flow deviation away from the front end module without providing the air guide at the top, and by providing air guides at the top, the flow is streamlined towards the front end module. So so this is a CFD analysis, CFD simulation which is done in ANSYS Fluent. So for measuring the airflow in the front end, we use vane type anemometer grids. So this, if you see, these grids, the small fans are mounted on the in front of the grid is made and is mounted on the front of the radiator. And this actually the RPM of the fan is calibrated to the velocity, front end velocity. So we measure the velocity at the different running conditions. So if you see at the LS side, the bumper cutouts, additional bumper cutout which you are seeing at the center was not there. So there was a flow recirculations were happening, and by providing the front end cutouts, the flow recirculation is reduced. So flow recirculation is a reversal in the reversal in the flow because of the creation of low pressure zones. So by providing sufficient cutout at the front of the vehicle, this flow recirculations can be avoided, and the total average flow also has, if you see, it has increased from 5.6 to 7 meter per second by providing the front cutout. So we do different development tests to ensure that the required flow at the front is available at the front end. So the bumper cutouts, fan sizing, everything is sufficient to meet the requirement at the vehicle level. So coming to the cabin airflow simulation, simulations are done to ensure that the required air velocity is available at different passenger seat position face level. So the vent position, vent size, vent angle, all these things are optimized to ensure that required airflow is available and air velocity is available at different seating position. If not required, additional vents are provided at the B pillar or maybe the C pillar area to ensure that there is sufficient airflow available in the different seating locations. And pressure drop simulations are done to ensure that the flow ducts, the air ducts which are used for taking air from the front end module to the B pillar or maybe the different locations, there is minimum pressure drop is happening, and we are achieving the required airflow at the passenger face level. So to measure the airflow at the passenger seat level, hot wear anemometers are used. So typically the vane type, the fan type which you saw before in front of the radiator, they are in size. So if you want to measure the airflow in a small area like the passenger face area, if you want to measure the airflow, we cannot mount multiple anemometers at that location, because of which these hot wear anemometers are used. So these anemometers are just like a which based works on the principle of hot element. There is a hot element, and air as the airflow increases, there will be more heat rejection, and air velocity is calibrated to the hot element current requirement to maintain the hot element temperature. What is the velocity requirement, sort of thing. So they are very small in size, and so we can mount multiple hot air anemometers at the face at the required position, and for measuring the airflow at the passenger face level, we are using the hot air anemometers, and this correlation is done with the actual CFD measurements which we are doing. So before the vehicle body is available, we are using rigs are used, like a closed enclosure. Like before, we are in the concept stage, and the body is not available. So these universal cabin airflow rigs are used to uh, simulate the to do different development tests for the vent position, vent angle, vent sizing, and at the different passenger seating position. So coming to thermal mannequin. So these thermal mannequins are a new development in the thermal system for the cabin comfort measurement. So typically, the cabin occupant thermal comfort depend in addition to temperature and air velocity. It depends upon mean radiant temperature. Mean radiant temperature is the temperature of the enclosure. Like when we are putting the vehicle for soaking in hot ambient, the enclosure temperature goes very high. Like the body temperatures goes to temperature like 60 or 70 degrees Celsius. So this mean radiant temperature also plays a important role. So these thermal mannequins are used to measure the mean radiant temperature, also mean temperature and operating temperature. Operating temperature is the average temperature of the cabin air and the enclosure. So these values are measured in addition to the air temperature and air velocity to calculate the occupant thermal comfort. So it calculates some value called PMV. PMV is the predicted mean volt. So like at a predicted mean volt of 0 means its occupant is neutral, and +1 means slightly warm, -1 means slightly cool. So by logging different parameters like air temperature, relative humidity, velocity, and the mean radiant temperature, it calculates this PMV value, so that it actually predicts thermal comfort of the occupant. So there are homologatory requirements to clear the, like in rainy season or in cold ambience, the mist is developed at the on the glass inside the glass. So there is a homologatory requirement to clear the mist which is generated on the windshield. So this is a safety requirement. So to meet this demisting, the vents are provided at the front IP area, and airflow is directed towards the windshield. Typically, we use um, heating the heater mode, so that the air is hot and the mists are get cleared. So windshield simulation is done. As per the requirement, the area A, which is the vision area in front of the driver, and area B, which is a total area, vision area of driver and co-driver. These two areas should be cleared within 10 minutes. Like 90% of the area A should be cleared in 10 minutes, and 80% of the area B should be demisted in 10 minutes. So these requirements are there. For the simulation, airflow simulations are done to ensure that there is required airflow is available on the NB area, and in the the vent angle, vent position, and are adjusted to ensure that there is a required airflow in the A and B area. So in actual testing of demist testing, actually, the test is done at -3 degrees Celsius in a cold chamber, and the mist is generated by a mist generator, and for 5 minutes, and then demist system is vehicle demist system is switched on, and then the mist which is generated on the windscreen should be cleared in 10 minutes. That's a requirement. So actual development testings are done in the climatic cold chamber, um, by initially vehicle is soaked at -3 degree around 10 to 12 hours, and then the mist is generated. You can see the mists are there at the inside surface of the glass, and then we mist is generated, and then our demisting system will be switched on, and markings are done, like what is the area cleared at different times, like 12 minutes, 20 minutes, 30 minutes. We mark the area which is cleared to check it is meeting the requirement. And thermal imaging cameras are used to measure the temperature over the entire surface. Like when we are measuring with the thermocouple, we are able to measure the temperature at only one point. So this thermal imaging camera can give a 3D 2D plot like we get in CFD. So these images, if you see, these are the images taken with the help of a thermal imaging camera. So these images help us to understand what is the temperature profile which is there on the windscreen, which is and we are able to analyze in case some area is not clear. These images help us to identify and optimize the demisting system of the vehicle. In addition to demisting, there is a requirement of defrost also. Defrost is like a ice formation at the front of the glass. So that test in that test also is done at -8 or -18 degrees Celsius, and the mist should be cleared in 40 minutes. That's the requirement for the demist performance testing. So this is the uh, exhaust simulation. So for exhaust, mostly the exhaust back pressure and the flow uniformity in over the surface of the different components like DOC, DPF, or these things are achieved with the exhaust simulation. So here you see the exhaust system CFD simulation which is done. So the here if you see the exhaust back pressure which is coming is 325 milli 325 and the exhaust pressure drop is reduced. Exhaust contribution of the individual components are reduced to achieve the required back pressure of millibar, like the 325 millibar. To reduce that, so higher the back pressure, it will eat away the engine power. So lower the back pressure is better. So the simulations are done to improve the back pressure and also to improve the flow uniformity above the components like DOC, DPF, etc., etc. Sorry. Yes. Okay. Underhood thermal simulations are done. Like at the underhood of the vehicle, thermal simulations are done to identify the hot spot which is coming, like near to the turbocharger or the hot engine, and to identify the requirement of heat shields. So here, if you see, there is a hotspot coming on the exhaust, near to the exhaust on the air cleaner. So the heat shields are provided on those area to ensure that there is no damage of the parts. So this was the underhood thermal simulation, and then even air intake, depression, and flow distribution simulations are done to check the pressure drop which is happening across the air intake system and the flow uniformity on the air cleaner. So the flow should be uniform on the air cleaner to ensure that we utilize the full capacity of the air cleaner. So simulations are done for the air intake system for reducing the air intake depression and flow distribution over the air cleaner. So coming to the end, this is a typical vehicle level DVP of DVP is nothing but the design validation plan. So after the in the design phase, there will be DFMEA will be done, design failure mode plan effect analysis. This is a document. This is done together with the design team and to understand what are the failure modes which can happen in the system, and then we identify the DVP. DVP is a list of tests which should be done on the vehicle to ensure that those failures are not coming. for the engine cooling system. So typical test involved the uh, coolant filling test, which involve expansion volume, deaeration test, and cooling fill test. So cooling fill test, this check that coolant is filled in the required time, and deaeration test, vehicle is run in idle condition to and air bubbles in we check with air bubbles with a transparent glass tube that the bubbles are getting cleared in the required time. And after heating, like a cooling system is getting heated, the degassing tank should provide required expansion volume, so that the coolant will not overspill from the system. And at the in the full heat up condition also, the system should provide the expansion volume to take up the expansion of the coolant. And water from flow is checked to whether it is meeting the required target, like 115 lpm at 4000 rpm, and airflow rate measurements are done, and engine cooling performance tests are done at a max speed and max torque condition. Even hot shut off test is done, like third gear towing, where the vehicle is pulled by another vehicle, and the engine will be to simulate the vehicle driving on hill or ghat conditions. Towing tests are done and to ensure that the cooling system is able to meet reduce the required amount of heat in the low velocity low velocity ghat driving high power conditions. And hot trips are done at Jaisalmer at the peak ambient of 55 degree, to ensure that coolant temperatures are within the limit, like 115 degree Celsius, and there is no overheat happening, and the cooling system is capable to reject the heat. Cold trials are also done to check the cabin heating performance, and at the cold performance, cold ambience done at Manali. Water wading tests are done at 150 and 350 water levels, to ensure that there is no failure of the electronic components. And then fan duty cycle measurements are done to check the fan, how much the fan is getting utilized in the different ambients. Though those tests are also done for the durability checking. ADT, accelerated durability trials, general highway durability, and high speed durability, city durability tests are done, where the vehicle is run like 1 to 2 lakh kilometers as per the customer driving cycle, to check for any failures which are happening in the vehicle. And SAM trials are system accessibility and maintainability, to check for the easy accessibility of the components for repair and maintenance of the vehicle. So here I come to end of my presentation. So I think that I was able to uh, I think I am able to present in a way. I think you are able to understand. If in case anybody has any doubt, they can ask. Actually, I pass it on to Subramaniam. It's like in case anyone has any doubt, they can ask.
Thanks, Vibin, for giving a very informative and knowledgeable webinar on vehicle thermal systems. So, participants have been exposed to the different areas where thermal management of automobile system is needed for effective performance. And you have discussed about EV vehicles, battery cooling, and how to do the simulation so that you can optimize your design and you can provide a enhanced thermal management for the vehicle. So it is a really a very informative webinar. So participants, if you are having any queries, feel free to ask, and I will be sharing the feedback link also, and you can fill your feedback so that we'll be delivering the e-certificate. And those who want to ask questions, you can ask the questions. Otherwise, you can put the message in chat box. I can ask questions on behalf of you. Any questions? Vivin, Pramod Shakkar is asked any research paper related to thermal engineering papers on automobile engineering.
Uh, like I have presented some papers on on the heat load calculation, cabin heat load calculation, that I myself have done one paper on IGISRT, and another paper I have done on vehicle performance. So a lot of papers are available in SAE. SAE, if you go through, a lot of research papers are there. And currently, because of the lot of new developments which is happening in the electric vehicle and HVAC and engine cooling system, there are a lot of papers which are available actually in the public domain. Like if you see in the internet, and I also have presented one or two papers for in the IJSRT.
Uh,
I
uh,
can share
okay,
if you
after
have any
this
specific.
webinar, can you share some basic research paper so that I can forward it
Yes,
to the participants? Okay.
yes, I'll share. I'll share.
Okay, and he's asking some journal name. Pramod Shakkar is
Uh,
asking.
Yes, actually, journal name, there are a lot of papers. Like if you go through, SAE is the one of the major, we get good quality papers. So and it depends. A lot of different researches are happening in different areas. Like if you see, HVAC system, cabin heating is a different area, and battery cooling is a different area. Now, lot of new technologies are happening, like coolant cooled, air cooled. So you can search based on your requirement, like what area you are looking at. So it is a very vast area. Like if you talk about engine cooling, that you will get a lot of papers on engine cooling, on the radiator sizing, or then you can if you see on the HVAC system, like for the cabin cooling, different developments are happening for battery cooling. Now a lot of developments are even happening for the hydrogen fuel cell vehicle. It is like papers, like first like suppose you are doing some, you are interested in some research in some particular area. So you want to identify like which area you are want to concentrate, maybe cabin cooling or radiator, or then once you finalize on this thing, then we can get lot of papers are available in public domain also. And once you have, you only thing to identify the like the area of your interest and selecting it. So that is which you are liking, so that is a thing. So a lot of developments are happening now almost in all OEMs, like EV vehicles. Like if you see, Tata is coming up with a lot of cars, like Mahindra is also coming, ForceMotors is also working on a lot of EV vehicles. A lot of developments are happening because a lot of even local suppliers are also bringing up with the parts. So a lot of developments are happening, and a lot of literatures are also available in the public domain. And even if you see, a lot of seminars are also happening. So if you are like if you are into LinkedIn and other like technical this thing, you will come to know about, and you will get the details of the. And I can also share, if you have any specific area, if you want to learn more, so I can also share you some technical purpose or details about those particular areas, like where you are interested.
Any more questions, participants? Okay, I think no more questions. So, on behalf of our institution, Sri Sastha Institute of Engineering and Technology, we thank our today's speaker, Mr. Vibin Jacob, Manager of Force Motors, for delivering a webinar for our institution as well as other institution students and industry professional. I I assume it will be more useful to all. And if you're having any further queries and other things related to thermal management, you can ask him. And after this webinar, I can, with his permission, I will share his email ID. So any queries related to thermal management or any internships in force motors and other things, you can feel free to ask. And I will point. Sorry, Vipin is one of the nice person. He will help the students community in getting internships, as well as he will intimate what are the opportunities possible for the automobile students also. So I will share his contact with you, so that if you're having any queries in thermal management or any internship in force motor or any direction you need as automobile engineer, definitely you will be guiding us, and you will be helping our student community well. So we will be closing this webinar. Thanks, Vibin, for delivering this webinar.
Thanks.
Let me close this.
Thanks, Surone, for giving.
Let me close this webinar.
Yes. Thanks, Subramanian, for giving me this opportunity, and I am really thankful that so many of people have taken that time to attend this webinar, and to they are. I'm happy to see that so much of people are interested in this thing. Thanks, Subramanian, for giving me opportunity.
Thank you, Vivin,
Really.
for giving the webinar,
Okay.
and thank you, participants,
Okay.
for attending this webinar. So we are scheduling another webinar on 31st August. I am expecting all the participants to attend, and I will be sharing all the content in email with you. Thank you for attending our webinar, participants, and please attend our webinar and make it as a more knowledge sharing a platform. Okay.